Hi, this is Eric White. A key aspect to developing general-purpose Open XML algorithms is testing. Attempting to write general-purpose code that will deal with all possible scenarios of Open XML documents is difficult. After finishing code and doing basic testing, invariably I find some situation that I haven't considered. I have three goals for Open XML code, such as revision acceptor, document builder, presentation builder, and such code. My first goal is, first and foremost, it should not throw exceptions or crash, except those exceptions that are documented and expected. We run Open XML code on servers, and it's not okay for that code to crash. I try hard to make the code not crash even if such code is past an invalid Open XML document. Second, if the code produces Open XML documents, such code as revision acceptor, document builder, or presentation builder, it should produce valid markup. It's not okay if the code produces invalid markup. Third, and this is in fact third on the list, is the code should do the right thing. This goal is behind the other two goals of it shouldn't crash and it should produce valid Open XML documents. Over the years, I've amassed a pretty big collection of Open XML documents. Some of them were contributed to me by other Open XML developers. Many of them I fabricated myself for specific testing scenarios. Many of them are documents that are posted in public locations on the web. Some of these documents are documents that I randomly modified programmatically for fuzzing tests. I have more or less about 1 million Open XML documents now. Before releasing a new version of Power Tools for Open XML, or the open source Open XML SDK, I run a series of tests across all of these documents. If, for instance, HTML converter doesn't ever crash or throw exceptions when transforming one of these 1 million documents, I can reasonably be sure that it won't crash when transforming your documents. But do you have any idea how long it takes to run HTML converter over that many documents? It literally takes days. However, if I spread this testing into multiple processes on multiple computers, I can reduce the time to run tests to about an hour. And this also gives me a great reason to have 10 quad-core computers in my office tied together with a gigabit network, and that's fun. It also means I don't have to feel guilty about buying a new quad-core laptop, even when the old one is still perfectly serviceable. I put the old one in the stack of testing laptops and I get to use the new one. Therefore, over the last period of time, I've been developing a harness for running Open XML code that is spread out over multiple machines. This code will become the core of the test harness for the Open XML SDK, as well as the test harness for Power Tools for Open XML. I call this system OxRunner. It is a system that enables hyper-parallel processing of Open XML documents. It's based on the .NET Framework 4.5, and it makes use of the MSMQ messaging system. It uses the Open XML SDK and Power Tools for Open XML. This screencast is a very long, deep dive into the internals of this system. Unless you have this specific need, I recommend that you do not watch this screencast. It is very detailed, discussing the various types of processes and queues that make up the system. To be honest, it is much a screencast recorded for me as for anyone else. I know I won't remember all of the details of this system when I next need to work on it, and I'll be able to watch this screencast and refresh my mind with the details. this screencast isn't perfectly organized. I was more concerned with capturing all of the technical details than I was with organizing this screencast as a coherent introduction into OxRunner. If you so care to, you can find OxRunner on GitHub at https://ericwhitedev/OxRunner. A couple of caveats about OxRunner. This system is under development. You can count on the fact that this will change in the future, and it may change in ways that are not backwards compatible. The location of this Git repo very well may change in the future after it becomes more mature. The third caveat is that I'm not in position right now to provide much support for this system. If you need support or help with the system, you can feel free to contact me directly at eric@ericwhite.com, and based on my consulting schedule and available time, I might be able to help you. So, you have been warned. In this screencast, I am going to go through the mechanism of the OxRunner system. The OxRunner systems enables ultra high performance Open XML computing. Open XML computing is CPU bound. This means that with the fast hard disks and solid state drives that we have these days, the time necessary to read and write to the disk is relatively minimal compared to the time that the Open XML SDK takes to run its code. If you run a single application on a machine as a single threaded application, you will see that the CPU time is only about 25% on a quad-core machine because it's only using one core out of the 4 cores. You can get a lot of performance improvements by making something that runs on more than one core. But the issue that we have right now is that the Open XML SDK isn't thread safe. This is due to the bug in system.io.packaging where isolated storage will use the same directory name for multiple threads, or it will use the same directory name for 2 executables that have the same strong name. So we deal with this in the same approach that I deal with this in the ultra high performance Open XML document modification example that is posted on Open XML Developer. The main enhancement in OxRunner is it has this ability to not only spread Open XML processing over multiple executables on one machine as the high performance Open XML document modification example does, but it has the capability to spread this over any number of other computers so that we get 7, 8, 10 or more computers all working on the same problem at the same time. For the terminology in this screencast in OxRunner, we have one computer that we call the master computer, and we have any number of computers that we call the client computers. And of course, the master computer itself can also be one of the clients. And in the simplest configuration, which I'm going to demonstrate in this screencast, you can even run this all just on one computer. There will be one master and one client all just on one computer. There are 4 programs that make up this system. There's the controller master, which is the program that you use to control things. It has the simplest user interface possible. You can specify what to do in that user interface. It's just a command line interface, and then that runs things on other computers and so on. This is how you kick off the process of running a run, as it were, that does a lot of Open XML work. I said there's 4 programs. There's the controller master that runs on the master computer. There's also ControllerDemons, and these run on all of the client computers, and the controller master tells tells the controller daemon to start a particular daemon. So in other words, there is also a runner master, and this is the main computer that organizes the work to be done, and then there's RunnerDemon, which actually does all of the work. So 4 programs: controller master, which you use the user interface to do stuff with. There's the controller daemon, which starts other daemons. There's the runner master, which controls the work to be done and figures out what needs to be done. And then there's the runner daemon, which actually does the work. The runner daemon is the only Open XML program in these 4 programs. The other 3 programs don't actually use the Open XML SDK at all. The controller daemon is designed so that it doesn't need to change very much at all. I expect that it's in its final form or very near to its final form right now. It's designed so that when I set up my whole set of computers to run Open XML tests, the computers will run the controller daemon upon booting, so it's always there, always ready to do work for the controller master whenever you run it specifically on the master computer. So I'll run the controller daemon. It's over there running and waiting for us to tell it what to do. Now I'll run the controller master, and as I said, it's got the super simple user interface. Let's look at this log here just a bit. We can see this log in a log file that it writes. Here's the controller master log file that I just wrote. The first thing that the controller master does is it looks for 3 queues, and if they exist, it clears them. If they don't exist, it creates them. The controller master queue is the queue that the controller daemon speaks to when the controller master tells the controller daemon to do some activity. Then the controller daemon will turn around and tell the controller master what it's done. There's also a controller master status queue, and when certain things happen on the controller daemon, it tells the controller master status about this. And I put this into a separate queue just because I want to receive messages on that queue in a separate thread and display those messages as appropriate. If I put them into the same thread and displayed what happened in that thread, it would disrupt the user interface in the controller master. So the controller master queue is where it receives messages from the controller daemon indicating that certain things happened that we're waiting for. The controller master status queue is for asynchronous events from the controller daemon, just indicating what has gone on, like if a process exited or something in the controller daemon. The controller master alive queue is there to speak to the runner master. When the controller master starts the runner master, it wants to make sure that the runner master is alive before it tells the controller daemon to start the runner daemons. So we want the master to come alive, and then we want to start the daemons on all of the client computers, and we don't want to start those daemons until the controller master is alive. So this controller master alive queue is for communicating back and forth to the runner master. One point here is it sets certain environment variables because it does compilation. It compiles the runner daemons and it compiles the runner master before running things, and this eliminates the issue where you pop over into the runner daemon and you make some small change to your Open XML code, and then you pop back into the controller master and run things, and if you forgot to compile the controller daemon, then you would be running your old code on all of the client computers, and this is there because this is what I used to do in the previous version of this, and it was very frustrating to me. So the controller master actually compiles the controller daemon and the master daemon before running them. Setting these environment variables, this is an activity that is specific to
to the version of Visual Studio that you're running. Right now this has only been validated to work with Visual Studio 2013. So when we get new versions of Visual Studio installed, these are going to change, and I know I might forget to update the setting of these environment variables, so I put it into the log file to remind me that when I get a new version of Visual Studio, I need to change controller master so that it sets the right environment variables. The next thing that the controller master does is it pings all of the active daemons. Active controller daemons is what that should be, to see who's alive, what client computers there are. And right now it comes back and tells us there's only one client computer running. To know the list of client computers, we look in this controller config file, and it has a list of all of the client computers that you might have running, and so the controller master pings all of the controller daemons, seeing who's alive so that it knows how many client computers it has at this point in time. And this would need to be updated for all of the client computers if you're running this on a different network. Let's go back to the controller master and run it again. At this command prompt, you specify a particular runner configuration file, and let's go look at that. The only one that I've put together right now is this run transform test file storage. We have this problem that the test file storage is kind of in a bit of a mess right now, so what we want to do is transform this into another form that is much more consistent and easy to work with. Let's look at this file. The first thing that this file does is it builds all the daemons with build multiple exes here, and this has to do with dealing with the isolated storage bug. That what this does is it builds any number based on a configuration of daemons, and before it builds each one, it updates the assembly version number and then builds it and then changes the name of that RunnerDemon executable. And what this does is this makes sure that each one of those daemons has a different strong name, and because it has a different strong name, then it will use a different directory in isolated storage, and everything will be happy and run properly. It won't get the isolated storage bug showing up. And then I have these various ifs here. I say if I'm running on my big i5-8 machine, then this means it's going to run with many client computers, and it looks for a certain location for the test file storage. It'll be on this directory share here, and then it looks for a certain catalog of all the files in that directory, and that's in this file here. So there are two arguments in this case to the runner master, and then it tells it to run all of the daemons on all of the client computers. So this is a command that goes from the controller master to the controller daemon, telling it to start the runner daemons that it finds in this directory. This star up here, it looks for that star, and if it sees it, it looks for any number of those runner daemons and runs them. If I'm running on a local machine like on this Asus T100, then it finds the test file storage in C:\\, and the second argument it looks for this small file list.txt, and this is just the file list of a smaller file list for testing purposes. So I have a much smaller test file storage on this local machine so that I can test things out and make things work. So this is there because I run this in kind of two basic configurations. One basic configuration is when I'm running it just on one machine and I'm debugging things and I'm building a particular test. And it also has the configuration when I'm running for real, as it were, when I'm running on many client computers and it's my intention to do a lot of work on many client computers. So up here, this is when I'm doing a lot of work. On these two bottoms is when I'm running on a development machine for debugging and testing purposes. So now I'll tell it to run XFM TFS. It next builds all of the daemons. We can see it building all the daemons. Of course, this doesn't happen so quickly because this is a not very powerful computer. It also built the run master. And when it finally got the ping and pong, when it sent the ping to runner master, it got a pong back from runner master. The runner master is then alive, and then it says do run to all of the controller daemons. All of those controller daemons then start up the runner daemons. When the runner daemons get started, then they send a runner daemon ready message to the runner master, and the runner master then tells it it's ready to do some work, and it sends a do message to all of the runner daemons, and the runner daemons do some work. And when the runner daemons are done doing work, then they send another message back to the runner master telling it, I did this amount of work, I processed X files or ran X tests or whatever it wants to tell to the runner master, and the runner master notes that, and then the runner master gives more work to the runner daemons, and they do more work, and again when they're complete they send a message back to the runner master telling it, yes, we're done. And then the process keeps on repeating until all the work. If you were observant, you would have noticed that the runner master, when it finally got done doing all of its work, it exited. A remaining item for me on my to-do list is that I'm going to have the runner master tell the controller master to kill all of the runner daemons. That's just a minor thing that I haven't taken care of yet, but once I get that particular item done, then at this point in time the controller master would be ready to run a completely different process. As it is right now, I can specify this kill processes command, and that kills all of the runner daemons on each of the client computers, only one in this case. If I look at this kill processes configuration file, we see it just tells it to just kill all of those runner daemons on each of the client computers. This is a command that gets sent to all of the controller daemons. The controller daemon then lists out all of the client processes that is running on its computer, and then it kills those processes. And then it did all of the work. Let's go up here. Right now I have things set up. So we saw the controller master log. This is the log written by the controller master. We also see there's this runner master log right here that gets written by the runner master, and then we see any number of runner daemon logs that get written by each of the runner daemons. There is an option in the runner master and runner daemons. Once things are debugged, we can tell it quit writing all of these log files. We don't necessarily need them if things are all working swimmingly. One key point to note is that in the situation as it exists right now, there is only one example of a runner master and runner daemon, this runner XFM TFS. Later on, there will be lots of these runners. There will be runners that can run any particular set of tests, and further we'll have it set up so that we can run whole piles of tests sequentially, one after another after another after another, so that when I make a change to the Open XML SDK and I want to just make sure that everything hangs together properly, I can run this massive test. It uses all of the client computers. It runs these tests spread out amongst all these computers, and when it gets done, I have a pretty good idea that the Open XML SDK hangs together properly. And when I get to that point, I'll be recording a new screencast, probably going through all of this material again. This is just an interim screencast. The purpose of this screencast is mostly for me so that I can remember how this all hangs together. It's a relatively complicated system with lots of moving parts. I know from past experience I'm not going to remember all of these details, so I can watch this screencast and refresh myself myself on all the details of how all of this works. Now I'm going to walk through some of the code here. I'll kill the controller master and kill the controller daemon at this point in time. We're done running code for now. I discussed what the three queues are up here at the top of this controller master and controller master log file. There's the controller master, which talks to the controller daemon, and the controller daemon replies back on the controller master. This is for things like pinging the controller daemons to see who's alive. There's the controller master status, and this is for asynchronous messages coming from the controller master daemon indicating certain events that happened. I've contemplated I may also use the controller master status queue for sending status messages from the controller daemon indicating performance of certain things. I also may do something like send messages from the runner master back to the controller master via this controller master status, giving information about performance, and also the runner daemon may send information back to the controller master status, also indicating information about performance, and that way I can provide continuously updated metrics on how things are going and when estimated time to complete is. There are two other queues out there. There are two principal uses of other queues. Let's go look at the runner master log. Here's the runner master log of that run that we just did. It's got the runner master queue, which uses to communicate with the runner daemon. There's also the runner master alive queue, which communicates back and forth to the controller master. At the moment, the only thing that's being sent on this is a ping and a pong from the ping from the controller master to the runner master, and then the runner master sends back a pong back to the controller master saying, I'm running and I'm ready to do work. We can see the log file. Here's the receive ping and sending pong. Then if we go to the runner daemon, I'll just pick the first runner daemon here. This is the run we just did. It noted that it created the runner daemon queue and the runner master queue, and the messages here are these runner daemon queue and runner master queue. This is where the message to do work and I've done work go back and forth. So the runner master tells the runner daemon, do some work. The runner daemon tells the runner master, I did it. And we can see here that the runner daemon received a do message, and it's adding these to a repo. I have a new idea of a document repo that stores documents via their SHA1 hash and also enables me to query that document repo based on certain characteristics. Much of that isn't implemented yet, but right now at least it's implemented to the point where it is able to store all of these documents in the repo. It stores them in a form that's relatively similar to how Git stores objects in the Git object database, in that it calculates the SHA1 hash, and then in a repo, let's go look at a repo just for posterity's sake. Here's a repo that it just created. It organizes all of the files in the repo, first of all, by extension, and then within extension it uses the first two characters of the SHA1 hash, and then within there it'll have all of the files stored via their SHA1 hash. These file names are missing the first two characters of the SHA1 hash. Those are the directory name. This is the same way that GitHub does things. In this way we prevent too many files from going into a single directory. There are cases where performance drops when you go above a certain threshold of use of files in a particular directory. I think that this is basically fixed in Windows these days, but I suspect that GitHub does this because there might be issues on Linux when you get 600,000 files in a single directory. So by doing this, we spread the files out amongst many subdirectories, and we never run into a situation of having too many files in a single directory. And we'll also notice here it has this moniker catalog.txt, and when I look at this, this has the complete SHA1 file right here, and then this moniker is the name of the file as far as the repo is concerned. This can be anything we want it to be. We can put any kind of name of a file in here, directory name, whatever, and then we can later on retrieve files based on their file name, and the way we would retrieve the file is we would find it in this file, and then once we found it we would get its hash, and then we would retrieve the actual file from the hash and return it to the process that wants that file to do some particular Open XML operation on that type of file. Now let's go through a bit of code. One thing that we will see here is there is this runner library here, and this runner library contains a lot of the nuts and bolts and plumbing of this whole system, and this won't change. We can use this library from any runner master and any runner daemon to do operations, and so the actual runner master and runner daemon are really short. Let's look at that. There's a runner master. Here's the actual implementation of this runner master. We see things like what is the repo name, what is the test file root location, what's the test file list, files to process, remaining files, the number of jobs, the number of client computers, and so on. But if we were to look at this, we see there's only 130 lines of code in this file. So this is a really short program because almost everything else is pushed out into this runner library over here, and almost everything in this file has to do with the particular task that you are implementing. So this particular implementation has all of the stuff necessary to go look at a particular big directory of Open XML documents and create a repo based on that. In another case where we're running some Open XML tests, this will all completely change and be associated with running any number of named tests and spreading out those over all kinds of client computers and client daemons or runner daemons. And then if I look at the runner daemon, this also makes use of all of the code in the runner library. You'll notice the runner master is a class that derives from this specific implementation of this runner master class. This runner master XFM TFS, or transform the test file storage, derives from the runner master class, and the runner daemon, the specific implementation of the runner daemon, derives from the runner daemon class. And if we look at this runner daemon, it's even shorter. It's 78 lines long, and all that it's concerned with here is when it gets going, it sends the RunnerDemon message, and then it goes into the RunnerDemon message loop, and then the RunnerDemon message loop looks for this do message and does some work, and then sends a work complete message. And that's all that's in this RunnerDemon. So this RunnerDemon is going to be a very short program. We're going to also modify this RunnerDemon program so that when you're putting together one of these things, you can just run it. You can F5 run it right from the Visual Studio and get everything working. It's not at that point yet, but that's to be coming. That's upcoming. You'll notice that the runner master and the runner daemon call into their base constructor. They have the same constructor as their base constructor, and that's where things actually initialize queues and all of the work that is common amongst any particular implementation of a runner master runner daemon pair. We can think of the runner master and runner daemon as being a pair of things that do a certain amount of work. And one point about this is that in the RunnerDemon we can see this message sent by the runner master, and then we can send the message from the RunnerDemon back to the runner master. If we come back over here to the runner master, we have this send files to daemon method, and if I look through the send files to daemon method, I see the configuration of this XML package here. This is the payload of the message going to the RunnerDemon, and this corresponds to the code right here to get information out of that payload. And then the RunnerDemon assembles its work complete payload right here, and that comes back to the runner master. And when the runner master sees the work complete message, the work that it does here is based on the payload from the RunnerDemon, and these will be specific to the particular runner master and RunnerDemon. These will change based on your needs of what the runner master needs to tell the RunnerDemon to do, and what the RunnerDemon tells when it finishes that work, and it tells it back to the runner master what it's done. One item that remains to be done is the runner master needs to assemble all of the results of all of this work into a run report and send that back to the controller master, and the controller master will then assemble all of those run reports from each of the runner masters into a run group report that I can then examine after running a massive set of tests, and we can see how things worked. This would be how I would tell that the Open XML SDK is ready to be released. If the run group report reports that there are no errors in any of the runs, then we can say, okay, we're good to go and we're ready to release the SDK. One point that isn't implemented right now, in the ControllerConfig.xml file, we have the ability to specify the number of RunnerDemons that should run on each client computer, and that's not implemented yet. That's to become. Right now that is not put there. Currently that's specified right here in the runner.cs. This is in the runner library. The runner.cs also defines certain constants, such as the names of all the queues. Here are all the queues. We have the controller master queue, the controller master status queue, the controller master alive queue, the controller daemon queue, the runner master queue, and the runner master is alive queue. Then we also specify the number of RunnerDemon processes per client. As necessary, I will read this out of the controller config.xml, and then we can tell a particular client that that client should only run 4 daemons or 2 daemons or whatever. Right now it's set up to run n daemons per client, and right now it's set to 5. Another thing, at this point in time, the information in this screencast is probably going to go fairly non-sequential. I'm just going to walk through the code and remind myself of all of the details about this code. We have this OXMessage, which takes a message as received by MSMQ, as sent by MSMQ, and puts it into the simplest form. We have the XML, which is the payload. We have a timeout, which indicates whether that message timed out, and we have the label, and we base what we do on the label of the message. We have this getQueueName method that we format the queue differently depending on whether we're putting the queue name together for a computer where the queue's on the same computer as the process, or if we're formatting the queue if the queue is on a different machine from this process. And this is just an artifact of MSMQ about how you have to put together names of queues. If you're talking to the queue locally, you have to use this format ./private $ and then the name of the queue. If you're putting together the message for a queue that sits on another computer, then you use this other name of the queue, this format name : direct equal OS, etc., etc. one note is we use private queues, and that's all that is necessary. In MSMQ, a private queue doesn't mean it's a queue that's private to a local machine. I'm not exactly sure what the distinction is between private and public queues are. Public queues might be, I don't even know what it's about, and they're not necessary to use. We have this ClearQueue message. When a queue already exists, it just goes through and receives messages until the queue is empty. We clear the queue upon starting processes. You can end up in this situation where something was sending messages to a particular queue while that process was dead or something, and you end up having those messages sit in the queues, and even if all your processes are exited, those messages are still in those queues because the queues actually live in the Windows operating system. They don't live in a process in any way, shape, or form. So when we initialize things, we clear the queue. One note for the future is I'm going to reduce the amount of time. Right now it waits for 1 second until, and that's not necessary. It could actually probably wait for a quarter of a second, and that will speed up starting of processes. If there are items in the queue, then it returns the message well before a quarter of a second, and so we can speed things up. And then there are the ReceiveMessage and SendMessage utility methods, and this ReceiveMessage, it may time out or it may not time out, and if it times out, it sets the timeout equal to true and returns it. If it doesn't time out, then one thing it does is it gets the label of the queue, it gets the label of the message, it gets the payload of the message and parses that as XML. And so this OxMessage contains just the information we really care about in the queue, and also put in a form that is more appropriate to this particular system. We don't really care about a lot of these other details about the queues. And when we send a message, we have the label of the message, we have the payload of the message coming in as an X element, we have the machine name that we're sending the message to, and the queue name of the queue that we want to send it to. And then this does the plumbing necessary to actually send the message. As long as we're talking about the runner master, let's look at the runner master file. This is the code that will be in common to all of the various implementations of runner master / RunnerDemon pairs. So this is the code for the runner master class that the specific runner master derives from. And we see here we have the queues for the runner master alive, the runner master queue. Here's the log that we're going to use. It initializes the log, and then anything that we send to the log method gets printed to the console and gets added to the log. Here's where we initialize the runner master queue, and if the runner master queue already exists, we just clear the queue. And then here's where we initialize the isAlive queue, and if it exists, we just clear the queue. Here's the message loop for the runner master, and the runner master looks for a message, and after it gets a message, it calls this process message, and this is an action that gets sent to the message loop. If we go back to the specific implementation here, we see that we pass in this lambda expression to the message loop, and this lambda expression just calls the process message in this module, and this is where we actually do the work. So that's the end of that story. Here's the receive ping send pong message, and this receives on the runner master isAlive queue up here, and it sends it on the controller master isAlive queue down here. So we've talked about this, we've talked about the message loop, we've talked about receive ping, receive pongs. One of the things here is we have this Divvy into jobs method, and if we go back up here in the specific implementation of the runner master, it's going to do a certain amount of work to figure out what is this particular runner master going to do, and it comes up with some kind of list of string where each string is a piece of work to do. It then calls this Divvy into jobs, which returns a list of string, and these are all of the jobs that are going to be done by each of the RunnerDemon processes. So we start off by putting lots and lots of things into each of the jobs in the RunnerDemon, and then as we get near to the end of running all of the jobs in the group, we start putting it into smaller and smaller units of work so that we don't end up in the situation where one particular RunnerDemon is out there and it still has 100 more documents to process, and we can't do anything until it's all done. That just gets a little tiresome. So I did some experiments to see if I just sent one message to do a piece of work and then get a message back saying the work was done, and that slowed things down considerably. So initially it starts out by processing 500 documents at a whack in the RunnerDemon, and then as we get nearer and nearer to the end, it starts cutting it down to smaller and smaller pieces until finally it's sending just a single piece of work at a time into each of the RunnerDemons. And that way, just as soon as all of the work is done, the runner master can quit. And at the same time, for the vast majority of the process of running a runner master and RunnerDemon, it's processing lots and lots of things at a time. It's processing 500 documents at a time until we get near the end. And this is a pretty good compromise for making it be as efficient as possible for me to run a particular set of jobs, so that largest amount of time it's processing 500 documents at a time. Then as we get to the end, it starts processing smaller and smaller until it's processing one document at a time, and then as soon as they're all done, you can see it quit. So this Divvy into jobs does that particular algorithm of creating a list of jobs with initially some number of jobs. You can see here, this is the algorithm that it uses to calculate the number of things to do in each job. We pass in the remaining items. We pass in the total work demons. This is how many demons are we dividing the work amongst. And then we pass in the maximum number of items per job, and you can see I passed in 500 right here. This is all hard-coded. I may get more sophisticated with this later on. We'll see. We'll just let that go as it is. As I said, this is an initial screencast. Later on, when this gets to its more final form, I'll run through this again, putting all of this information into a screencast that reflects a more sophisticated implementation of this. So now we've talked about Divvy into jobs, and there's calculate items in the current job. All there is in this runner master abstract base class of a specific implementation of a runner master. Let's go now look at the RunnerDemon. So going at the top of this RunnerDemon, the first thing it does when it comes alive is it says, okay, I'm ready to do work. And this is the first piece of communication between a RunnerDemon and a runner master. This is when the RunnerDemon says, okay, I'm alive and I'm ready to do something, and then it goes into its message loop. In its message loop, it waits for a do message, and here's, as I said, here's the payload of that message where it's going to tell it to do something, whatever it is it's going to do. And then here's the message that it sends back saying, I've done. And that's all there is in this RunnerDemon. Let's look at the RunnerDemon base class. In the base class, one thing that we do is we have a daemon message that we're going to send back to the runner master, and this daemon message is, we need to tell the runner master what the RunnerDemon machine name is and the RunnerDemon queue name is. So one thing that the runner master sends in the payload is that it sends one thing. We'll notice this RunnerDemon has the runner master machine name and the short minor revision number. So these RunnerDemon, their queue names are based on the minor revision number of the particular assembly that's running, because we're going to have 5 or n number of daemons running on a particular client. Each one of those is going to have a different queue, and we need to have those queues have a unique name. So this is where we get the assembly minor revision number, and this is the number that was created for each executable separately in the compilation process that I referred to earlier in the screencast. And one thing is the runner master machine name. This gets passed in as an argument to the RunnerDemon, so that's how the RunnerDemon knows what machine to send its ready message to. So when the client daemon runs the RunnerDemon, it tells it what the runner master machine name is as an argument to the command line, because otherwise the RunnerDemon would have no idea of who to talk to. So the arguments here are interesting in that the client master tells the client daemon to run some RunnerDemons. The client master, when it tells the client daemon to run the RunnerDemons, it tells it what the master machine name is. So therefore the client daemon tells the RunnerDemon via a command line argument, here is what the master machine name is. When the controller master tells the ControllerDemon to run a RunnerDemon, the controller master sends the master machine name to the ControllerDemon. When the ControllerDemon runs the RunnerDemon, it tells the RunnerDemon what the master machine name is via a command line argument. And so that's why we have this line right here where we tell the RunnerDemon what the master machine name is. Then when we initialize, or when we call the constructor for the RunnerDemon, we pass in the runner master machine name and we pass in the minor revision number of the assembly, and therefore we can create the queue with the appropriate name. And here's a simple little method to send the daemon ready message. The message label is RunnerDemon ready. It sends the runner master machine name and it sends the runner master queue name to this send message. Here is the thing. It creates the RunnerDemon queue, and if it already exists, it just clears it. And all it does is initialize the runner master queue. Going back to this runner module, it's interesting to note, so the controller master creates the controller master queue, the controller master status queue, and the controller master alive queue. The ControllerDemon creates the ControllerDemon queue. The RunnerDemon creates the RunnerDemon queue, and the runner master creates the runner master queue and the runner master alive queue. So there are two situations. One case is where you create the queue and each one of those has the responsibilities as I've just listed it, and the other is just where you initialize the queue or look for an existing queue, and then all we do is, in some cases we clear it, like when you run the controller master, we can clear all the queues. In other cases, all it does is create a queue. It can't clear the queue. It's going to be looking for messages on that queue, and someone else is responsible for creating and putting messages in the queue. So here's a case where when creating the runner master queue, all we want to do is initialize it. We don't want to create it and we don't want to clear it. And here's a little method to receive the OX message from the runner.receiveMessage method. At this point in time, we've talked about everything in the RunnerDemon class. So we've talked about the runner master class, we've talked about the RunnerDemon class, we've talked about the runner class. There's the repo class. That's not really relevant to this. This is particular to putting together the repo. I'll go through it really quickly. This is, it creates the moniker catalog if it needs to. And here is the one method in there to get the hash code of the file and create the directory for the extension. And then once it's created the directory for the extension, it creates the directory for the first two characters of the hash code, and then it copies the file in there. I have this files utils method, and the various methods in the system.io namespace are all thread safe, so they will never fail in some unhappy way if multiple processes try to do things to them. However, they can throw an IOException if another process is doing something. So therefore, when we do things like create a directory, we have this thread safe create directory method that watches for the IOException, and if it sees such an exception, it just sleeps for 50 milliseconds and then goes back through and does it again. And that way we can have lots and lots of processes doing things on the same directory structure and nothing ever breaks. The worst thing that we have is we have a small performance hit if two separate processes try to do the same thing at the same time. It's rare that this would happen. It's rare that this sleep for 50 milliseconds would be called, so therefore the performance hit is really acceptable. And we have, this is used for things like updating that moniker file. And we have some other utilities like get files recursive to list out all the files in a certain directory, or so on and so forth. So we've talked about RunnerMaster, RunnerDemon, RunnerRepo, file utils, RunnerLog, not much there. There's Executable Runner. This is the same class that's in Power Tools for Open XML. And console position, this is just to set up the position of the various console things so they aren't overlapping. That'll probably get more sophisticated as we go into the future. So we've talked about the RunnerMaster and RunnerDemon in depth. Let's see if there's anything that I want to talk about. One thing is there's only ever one controller master and there's only ever one controller daemon, so I didn't set these up so that these derive from an abstract base class like I did with the RunnerMaster and RunnerDemon. All of the function is just right here in the controller master. Let's just look through and see if there's anything interesting. We read the controller configuration, we set up the console file, we initialize log, we initialize queues. This is all same more or less as in the RunnerMaster and RunnerDemon. We set up the environment variables for compilation. This is where things will change when I go to a new version of Visual Studio as necessary. We'll change this. We get the active daemons. This is where the controller master finds out how many controller daemons are running. We start the status thread that is going to receive asynchronous messages from the controller daemon or anyone else who wants to send things to the controller master. And then we get and run command, and this is the thing where we have the little user interface that gets the name of that command file, XML file, and then runs all of the commands in that XML file. Let's see if there's anything in here. The read controller fig, nothing there. Initialize log, that's pretty simple. Set up the console window, that's simple. Start the status thread, pretty simple. .NET threading. This just receives messages and kind of prints to console everything that happens. The get and run command, it gets the command, finds the appropriate file, and then does run command. One thing that this does is when we're writing the log and when we're exiting the controller master, the last thing it does is it fires up the editor as specified, and so that we can just look at the log when we're all done. The run command loads the command file and then iterates through each of the commands, and it does run one command. And the reason this is there is the if command actually does run one command recursively. Here's the thing to build multiple exes, and then it calls this build multiple exes, and there's not a lot there other than firing off the executable to run ms build for that particular directory. It's pretty fiddly to get that all working, but there's nothing there that is very esoteric. And if we see the runner master, then we build that guy. We do things like look for, if it's there, try to delete it, and if we can't delete it, then the runner master might still be running. And so this is all set up so that any time that run one command returns false, it just aborts processing. So this way, if something happens when you're trying to run one of those command file XML files and something doesn't work, we can just stop the whole process and say, oh, it's broken. And here, after we killed the executable, then we can build executable using ms build. Here's this ms build path that'll probably change in some future version of Visual Studio. And if it fails in its build, it prints this to the console and to the log as appropriate and returns false and aborts things. And then if it did build properly, then it starts the runner master right here. And here is the other end of the send ping receive pong. This sends a ping. One interesting thing here is we can get a message queue exception here if the runner master is not even created as queue yet. The runner master has to create its queue before we can send a message to it. So if this happens, we wait a second and then try again. We actually could see that when we were running the controller master, we could see that it was waiting for the runner master to get going. And this is important because the runner master may have several seconds of work to do to get ready to run. It may need to do something like read a list of 600,000 documents and divvy those up into jobs and things like that. In that process, it needs to get all ready so it's really ready to do work before we start the runner daemons. So that's why this send ping to the runner master and receive the pong from the runner master, that's important. There are various internal exceptions that could happen here. In the future, this shouldn't just throw an exception. If we didn't receive the pong, we should just report this to the log file and let the controller master continue on its way. Same thing here, building an invalid or the invalid executable path. This should just report an error and return. Right now it just throws an exception. This will be enhanced. One thing that we can do in the controller master is we can tell it we want to list all the controller daemons on all the machines. And one thing here is if it's not one of these other messages that we know about, in other words, we have these build multiple exes and we have the if and the runner master, if it's not one of those, then we just send that command to all of the active daemons. Here we just send the same command to the active daemon. So this way, if it's just some command like the run command, it just gets sent to all of the active daemons. Here's the build multiple exes. Here's setup environment variable. Here's this update assembly information. This sets the assembly information to a different number, different minor version for each of those daemons as we're building them. And this is setup environment variable if necessary. If these variables are already set up, we don't need to do it again. Here's the get command that gets the user interface via console.readline. Here's get all of the active daemons and create the list of the active daemons. And the way that this works is it sends the ping to each of the daemons and gets the pong back from those daemons and then creates a list of the active daemon. Update console. We have to do this thing in this controller master where we keep all of the console output in a list of stuff and then we update it so that way the separate thread can also be adding console output, but then we're inputting just on the fourth line from the bottom. That's how we can have a multi-threaded application that both threads need to print to the console. Here's our initialize or clear queues stuff. This initializes all of the 3 queues that the controller master will run, and that's all there is in the controller master. Now we're going to go to the controller daemon, go up to the top here, and setting up the console. We initialize the controller daemon and then go into the message loop, and if I go to this init method, this just initializes, this either creates the queue or just gets and clears the queue for the controller daemon queue. If the controller daemon queue already exists, we don't recreate it, we just clear it. And in this message loop, we wait for the various messages. If we receive the ping, then we send a pong. And this is so that the controller master knows that this daemon is alive. If we receive a do message, and if it's a run message, then we look here, and if the exe contains the star, then we run through and we run the executable for each one of those daemons. And that's how multiple daemons get started up on the client computer. If we have the list processes, then we call if the list processes contains a star, then we go and see how many runner daemons. We look for each runner daemon process in turn, and then we add it to the list, and then in the end we assemble a message back to the controller master telling it all of the processes that are running. And here's the kill processes, does a similar thing. It looks for that star, looks for each one of those runner daemons one at a time. If it finds them, it kills them. This run1exe, this is the thing when the controller master tells the controller daemon to run a runner daemon, then this run1exe gets run. It does a couple of things. It sets up an event for the process so that when that process exits, it sends a message back to the controller master, and you'll notice here it sends it back on the controller master status queue because this is a message that will be received asynchronously. If through some circumstance that process didn't start, then we send that back to the controller master status queue. It's not catastrophic if one of the runner daemons didn't start. It just means that runner daemon isn't there and is not going to tell the runner master that it's ready and it's going to do work, and then the runner master can't tell it to do work. So this would just be a reduction in functionality. To date, I don't ever see this being fired right now. I don't have any situation where that's being fired, but it is possible that it could happen. So therefore, at least I want to note that it could happen so that it isn't just a mystery as to some particular runner daemon isn't starting up. And then when the controller daemon does start the runner daemon, it tells the controller master, yes, the controller daemon did start such and such a runner daemon. And here's the initialize. So there we've walked through all of the code in the system. Mainly, as I said, it's particularly important for me. I don't think anybody else is ever going to watch this video, really, to tell you the truth. If you are someone other than me who watched this video, other than Navaneet, well, congratulations. One more thing to note. It's useful to talk about command line arguments. So when the controller master starts, it has no command line arguments. When the controller daemon starts, it has no command line argument. They just run. When the controller master starts the runner master, when the controller master starts the runner master, one thing that it does is it passes in these arguments. So here are the arguments to the runner master right here. So the runner master does have arguments, and they come from this config file, this run group configuration file. The other thing that the controller master does when it runs the runner master is it tells how many client computers are running so that the runner master can use that value in its calculation of how to divvy up into jobs. It also passes in the argument from the configuration file. So those are the arguments to the runner master, and that's how that runner master gets that information. When the ControllerDemon starts the RunnerDemon, it has one argument, which is the runner master machine name. And that's how the RunnerDemon knows to go and figure out who its runner master is, who that queue, what that queue is, what that queue name is. So that's how that gets initialized. So to summarize, the controller master has no command line arguments. The ControllerDemon has no command line argument. The runner master has command line arguments of how many controller demons there are, and the runner master has command line arguments that further come from the run group configuration file that we saw. And the RunnerDemon has one command line argument, and that's the name of the runner master machine name, so that it can tell the runner master machine name that it's ready to do work. Important to note all of that. I'm guessing that those are going to be enhanced in the future. I'm guessing that, but I'm guessing there will be changes to that. But we'll see. That's all.